Welcome to today's presentation. I'm Jay, your host, and I'm an investor with interest in semiconductors. Today's presentation is about silicon carbides. It is a semiconductor material with potential to gain massive traction in coming years. Traditionally, silicon has been widely used in semiconductors to manufacture electronic components. However, it is not the best choice for all use cases, especially in the area of high-power devices, electric vehicles, and inverters in solar panels. This is where silicon carbide shines with its performance and has potential to take significant market share from silicon-based devices. Silicon carbide is a rare compound, but it can be synthesized in a controlled environment. However, the manufacturing process is not easy. There are quality issues and wafer defects impacting yields. This presentation will highlight some of those issues. Looking at it from an investment angle, silicon carbide market is growing at 29% per year. According to Yole Development, a French consultancy, the market will reach 2 billion by 2024. As is the case with any disruption, there will be winners and there will be losers. Tremendous value will be created in this field, and hence it is high time to explore this area for potential investments. We are excited to have with us Dr. Peter Gammon. He is an associate professor at University of Warwick. He has been at the cutting edge research in this field for more than a decade. And his expertise include MOSFETs, IGBTs, and high voltage silicon carbide devices. Today, he will be taking us on a journey, starting with the basics of this material, manufacturing processes, quality issues, and major players in this market. Without further ado, I will hand over to Dr. Peter for our main presentation. Dr. Peter.
Thanks, Jay. That's very kind. Thanks for the great introduction. Yes, let's start on this journey from silicon carbide power devices, from the materials all the way up to the applications. Just a quick introduction to me. I'm an associate professor at the University of Warwick, and I've specialized in the development of silicon carbide power devices for about 15 years now. I do all the things an academic's supposed to do. I publish a lot of papers and book chapters and things. And our group is about 8 strong in terms of PhD students and postdoctoral researchers. And I'll be telling you more on my research later. But it covers silicon carbide as a material, silicon carbide devices, and into the application space as well. So I'm going to start by way of introduction by looking at the power devices market. And Jay said in his introduction about Yole Development. Well, I've also used a few of their slides, which I'll come to in the next couple of slides. So first of all, the application space. You can see a cartoon graph on the slides with power plotted against the frequency of operation. And we can map onto this the applications that are of interest to the power electronics space. And so we have at the high frequency, low power end, we have switch mode power supplies. And so you'll be familiar with these in your laptop or in your TV. These are converting the AC coming into your house into the DC that your laptop or TV requires. Higher up the power, slightly lower in frequency, we have the PV inverters. That's taking the DC power that's produced by solar panels and converting it into AC power for the grid. Electric vehicles, and we'll be touching on that quite a bit later. Electric vehicles have applications in both converting the DC battery power that's stored on board into usable AC power for the motor drive, and also in the charging infrastructure as well. The lion's share of the market is in industrial machines and drives, and that will take up quite a large chunk of the market currently. And going higher and higher in voltage, we get to traction inverters, and potentially right at the top there is the very high voltage grid infrastructure with an increasing need these days to move around energy over large distances, where we're trying to get our renewable energies from its source to where it's usefully used. And so, by way of introduction, let's have a look at how those applications map onto the market. You can see the big chunks there, motor drives, the industrial machines side of this are currently the largest, but the biggest markets in terms of the growth are possibly the smallest dots on this potential market growth. So over here we've got the market as it was in 2018. On the right hand side, the market as it is predicted to be by Yole in 2024. And the biggest areas of growth are the electric vehicle market and the charging infrastructure, both of which look like they could triple in the next 5 years. Standing strong amongst those are things like the uninterruptible power supplies, the motor drives, and the photovoltaic infrastructure, all of which are driving 21st century technology. Moving on, coming down a step in the supply chain, let's have a look at the devices that are going into those applications. And so the inverters require the power devices to do the switching within them. And on this, we have the 2018 picture on the left. On the right, we've got the 2024 picture with everything from silicon MOSFETs to IGBTs, silicon carbide MOSFETs, thyristors. These span that voltage versus frequency range that we were looking at in the last couple of slides. Again, this presentation is concentrating on the silicon carbide devices, and you will see that the MOSFETs, this thin wedge here, and the MOSFET modules, they are tiny proportions of this market today. But look how much they grow in 5 years' time. They are the fastest expanding, the fastest growing area in the power devices market today. And if one was to consider what the achievable market might be for silicon carbide, the direct competitor with the silicon carbide MOSFET is the IGBTs. So the IGBT modules, or the IGBT discretes, are these big chunks to the left of the silicon carbide devices and modules, and that's the potential market there for the silicon carbide devices in the future. This is a little bit more dated, this slide, but it's still relevant in that for years now we've been told that silicon carbide is on the crest of a boom, and there's been steady growth in the market for a number of years, but it's really looking like it will take off in the forthcoming years. And again, a lot of these slices are fairly steady, but the ones that are significantly growing are the PV and the electric vehicle charging and inverter infrastructure. Those are the slices that are consistently getting larger through this period, and so that's really what's driving the current war of attrition within the silicon carbide market today. Okay, what I'm going to do now is I'm going to go through the power devices and look at them in a generic sense, so that we can see what we want from a generic power device before we can introduce the benefits of silicon carbide power devices. So here we have a transistor, and it has two key states. It's going to be in its on state and in its off state. First of all, in its off state, we want it to be able to sustain, ideally, as large a voltage as it possibly can without breaking down. At some point, you put enough voltage across anything, it's going to go bang, but we'd like that to be as high a voltage as it possibly can. Whilst it is off, we'd also like it to conduct, ideally, zero current. In the on state, we want the device to be fully open. We want it to conduct maximum current with minimum voltage being dropped across it. That way, the power being dropped in that transistor is minimal compared to the power it's delivering to whatever it is, our vehicle drive system or our electric motor, whatever it is. So in order to achieve that, our transistor must have a minimum resistance. So this is our trade-off going forward. We've got to try and maximize breakdown voltage whilst we're minimizing resistance. Unfortunately for us, those two are a natural trade-off, and here we've got to introduce the material in itself. And so any power device is made up of a structural support, the substrate, onto which we're going to grow the active area of the device, the drift region, which is shown on the right with the title epitaxy. And so that's the process that we go through. Epitaxy is the process we go through to be able to grow this this thick region, which can be anywhere from 5 to 300 microns, depending on the voltage of the device. And that's going to support our voltage. But the thickness of that has two implications. Here we introduce the equation for the on resistance on the left and the breakdown voltage for the right. Now, we're not going to worry about what each of those components of that are in particular today, but just note that in order to minimize our on resistance, that drift region width should be as small as possible, but to maximize our breakdown voltage, it should be as wide as it possibly can. So we can either have a nice thin device with low resistance, or we can have a nice thick device with that maximizes our breakdown voltage. And so this introduces a fairly simple graph in which we've got our on resistance on the y-axis plotted against our breakdown voltage. And that line that's on that graph represents the minimum resistance that a device could have whilst achieving the voltage. And so the voltage is going to be dictated by the application. It might be that your motor drive needs to run with 1,000 volts, or it might be that it needs to run with 100 volts. But if it does, then there's only so much we can do in terms of the resistance. So we can plot on top of that graph what is basically the silicon market. We've got over the left here, we've got our silicon MOSFETs and Schottky diodes, and they sit above that line. There's nothing they can do to get underneath it. They are stuck above that limit, but they switch very, very fast, and they're going to be very little loss in terms of switching on and off. Underneath that line at higher voltage, you have the IGBTs and thyristors. They are higher voltage devices. And we play a trick with those devices to be able to allow them to drop just below this fundamental limit. But the price we play is that they switch very slowly and with some degree of energy loss compared to our MOSFETs over there. So this graph now resembles the power devices market as it looked in the early 2000s. With a choice between silicon or silicon. We either have the low voltage, fast switching silicon MOSFETs on the left, or we have the high voltage, slow switching bipolar thyristors and IGBTs on the right. So that leads us to neatly onto why we want silicon carbide and how that can interrupt that status quo. Coming back to this slide that we introduced before, trading off our on resistance and our breakdown voltage. Now, what we can do is we can play around with another component of the breakdown voltage equation down here. And what we've done there is we've replaced silicon with silicon carbide. And when anybody talks to you about a wide bandgap semiconductor, be that silicon carbide, gallium nitride, diamond, the chief motivating factor for those wide bandgap semiconductors is not their wide bandgap, it's not their thermal properties, it is this value, it's their critical electric field. Their critical electric field is measured in volts per centimeter. How many volts can the material withstand in a unit length of space? And so the big win from silicon carbide is that it can withstand 9 times the voltage in a unit space than silicon can. And so that's very helpful when we then go back to our unipolar plot that we had before. Here it is, because that now introduces a second line all the way down in that bottom right-hand corner. So now, where previously we were trying to optimize our devices to the black line at the top left there, now we've got a new point that we can shift down towards, and we can try and produce 1,000-volt devices at much lower resistance, for example. So we have 2 ways of exploiting this, and we're going to look at these in turn. So previously, we had MOSFETs and diodes that might have been sitting up here, where they're shown above the black line. They were made entirely out of silicon. And represented next to the graph is our silicon substrate with 100 microns of epitaxy on the top. 100 microns of epitaxy gives us quite a significant loss in terms of our resistance. And so we're going to lose a lot of energy in running that device just through the resistance of it. Let's utilize that in 2 different ways. So the first way we're going to do is we're going to keep our device exactly the same in terms of how we've built it. We've now just built it out of silicon carbide. We've produced it out of silicon carbide. It's the same thickness, but now, without doing anything else to it, the resistance might remain the same because it's the same thickness, but now the breakdown voltage is 10 times higher. So for the same device design, we end up with a 10 times win in the breakdown voltage. However, as a designer, that's not greatly helpful. I don't particularly need a 12,000 volt device where previously I was using a 1200 volt device. So rather, I would like you to replace my 1200 volt device with the same if possible. So in this sense, now we're going to look at how we do that. So we take our 1200 volt device that we had before, and we're now going to produce the silicon carbide device, but it's going to be 10 times thinner than the silicon device was before. The doping now of that region, the number of dopants that we put in there is also increased. So our resistance has about 100-fold reduction compared to our previous silicon device that we had there. So now we've shifted our silicon MOSFET and Schottky diode down to their new unipolar position down at the bottom of the graph there. So the power devices market, as it was in early 2000s, can now be updated. There's the 2002 market, and we can update that now with the silicon carbide market as it stands today. And now on the market today, between about 600 volts and 1700 volts, we have these fast switching MOSFETs and Schottky diodes that sit at the bottom of this graph, where previously there were only slow switching silicon IGBTs. So we go through all of that process so that we end up with a transistor that now is able to switch much faster than the IGBTs that we had previously. Why do we want fast switching? Well, fast switching has a big impact on the system later. So the main thing that we're trying to do with an inverter is we're taking a DC input and we're trying to produce an AC output. And we're going to be switching our devices on and off to try and represent that AC output at the end of the day. If you switch slowly, well, it might look something like an AC wave when you're done switching them on and off, but you're going to need large passive components, capacitors or inductors, to smooth that out again. And the bigger those components are, the larger your solution is going to be. And so if you can switch very, very fast, as you can now do with silicon carbide, your AC waveform when you're done with the switching stage looks a lot like an AC wave to start off with. You need minimum passive components, small capacitors, small inductors to smooth that out again. The case in point is here with a Formula E team, Venturi. Here's their progression with their inverters over the course of 2 seasons. In the first season, or the legacy from the season before, was an inverter of 15 kilograms that was being used to take their DC battery power and convert it into AC for their motor drive. In the first season after that, they introduced diodes, SBDs, Schottky barrier diodes, replacing the silicon diodes that were on board previously. And with just that one change, they managed to strip out 2 kilograms and 19% of size, just by having the ability to switch slightly faster with slightly less losses. The cooling requirement was less, and they managed to shrink it down slightly. In the final module, in the second season, they go to a fully silicon carbide solution, replacing the silicon IGBTs with silicon carbide MOSFETs. They strip out a further 4 kilograms, reduce it 30% in size, such that in the third season, your final solution is 9 kilograms compared to the 15 kilograms that you started with. And you won't need me to explain to you how important that is in something like high-end sports racing. So why silicon carbide? Here's a summary. I've only touched here on the critical electric field. A critical electric field can be used to either give you the higher voltage, as I mentioned, or you can drive up the switching speeds, or you can use it to optimize the efficiency of your inverter, or you could potentially use it a mix of all three, such that you're getting the benefits for the solution in question. A wide bandgap semiconductor such as silicon carbide has a much greater thermal conductivity and a wider bandgap than silicon as well. These two things both help the thermal performance. It is both able to conduct heat away from itself very easily, efficiently, and it is able to go to much higher operating temperatures than silicon can if the package that you put it in, the box that you put it in, allows you to do so. So potentially with every silicon carbide solution, there's the added benefit of needing less cooling. You need less cooling infrastructure if your devices can run hotter. As from a material standpoint, silicon carbide has some of the benefits of silicon as well. It's a freestanding substrate. You don't have to grow it on anything like you do with gallium nitride. And it can also be oxidized. With all of these MOSFETs, you have to produce the MOS region, the gate region, which is a metal oxide semiconductor. And the first fabrication process to achieve that is in oxidizing the semiconductor surface. And so you can form this natural insulator, silicon dioxide, with both silicon and silicon carbide. As Jay alluded to in his introduction, though, there are still challenges. I'd say that this is a fast maturing market, but there are still a few things that require work. The first is, most obviously, if you go to buy a silicon carbide device, then you will notice that there is a price differential here, and we'll touch on some of the reasons why. So a silicon IGBT as of yesterday cost no more than £4, with the equivalently rated silicon carbide device costing more than double that at £9.40. So there is an increase in unit cost of the transistor, but I think it's a bit of a blunt instrument just to look at that in isolation. If that results in less cooling infrastructure in a smaller solution, a more efficient solution, then at a systems level, we have to decide what price that pays back. So I think it's unfair to think to suggest that there might ever be parity with silicon as well, given the maturity of the silicon market. One of the chief drivers of the price is the substrate size that's available. I'm going to mix up both imperial and metric measurements here to be confusing, but silicon carbide is largely produced on 150 millimeter substrates. That's the predominant substrate size. Some are still using 100 millimeter, but the majority of the large scale manufacturers are producing 150 millimeters. For reference, that's 6 inches, and silicon is typically being produced at around about 12 inches or bigger. So the number of devices that are produced in a single run in silicon carbide currently is much less than can currently be produced in silicon. Most wafer manufacturers have announced or shown or demonstrated their 200 millimeter wafers, yet it always takes time with a new wafer size for the wafer quality to catch up with the generation before. So they have been announced, but it will take time for them to get to a good enough quality to be used in a chip manufacturing process. But as it does, as you go to 8-inch, potentially bigger in the future beyond that, that will have an effect on the price. Wafer quality is, if I'm honest, not bad today. It's good and it's getting better. What used to be called the killer defects within silicon carbide have largely been eradicated. There was a horrible thing called a micropipe that used to go all the way through that drift region and short out your devices, which meant your yield of your devices was negatively affected. Today, they are all but eradicated, and those that are still there tend to be around the unusable edges of the wafers. So that's not typically a problem today. There is a lot of work, however, that's needed to reduce some of the other defect types. But today, the diodes and the MOSFETs that are out there are of a pretty good quality. And the wafer quality issue impacts the future devices that might come from silicon carbide more than things like the MOSFETs and the diodes, which are in a pretty good place today. I'll revisit that in the next slide. Reliability, it's still a relatively new product on the market, and with the new products that as they come out, they need time in the field. There's no substitute for time in the field to improve the reliability, which will get more devices out in the field. That cycle is ongoing, but with the adoption of silicon carbide by some big and well-known cases, I'll come to Tesla later, and obviously there are a lot more less high profile applications areas than that. With all of the data that's coming back from in-field use, this is an improving picture and reliability is improving. Yet there are still a couple of known issues within the industry in terms of gate reliability and issues with something called bipolar degradation, which can cause issues if you use the inbuilt diode within a MOSFET. Currently, there is also a limited device range. You have the diodes and the MOSFETs available from 600 volts to 1700 volts. That could expand to 3.3 kilovolts in the next couple of years. There's already a couple of smaller manufacturers such as GeneSiC, for example, a fabulous semiconductor company, who are producing 3.3 kV devices, but that appears ripe for happening in the next couple of years, an increase in range. But there are not yet the bipolar devices out there. So where I'm saying there are silicon IGBTs, silicon thyristors, they tend to be in the low thousands of volts rating. In silicon carbide, those same devices can be produced, but they would be produced up to 30, 40, 50,000 volts in a single chip, with applications in electricity transmission, but they're not there yet. And that's what we need the maturity of the material to happen, to get rid of the last defects in the material to enable. The unipolar devices, these fast switching MOSFETs and Schottky diodes at the voltage range 600 volts to 1700 volts are exactly what's required for example, the PV market, the automotive market. That's why the manufacturers are concentrating in that area. And that's where the bulk of sales will always be in silicon carbide power. Is there a threat from gallium nitride? Personally, and I think a lot of people in the know would suggest probably not. Not through any weakness of gallium nitride. It's a very good material, has a very good threat to the market, to silicon in and of itself, but just in a different place, in a different space. Gallium nitride, I think most of us tend to agree, will see a lot of penetration into the RF market, potentially into the low voltage power sectors. But where we're starting with silicon carbide from 600 volts upwards, the potential for gallium nitride is really 1200 volts downwards. So there might be slight crossover, but I consider they have their own markets and their own potential benefits in different spaces. And so Jay's asked me to take a look at the supply chain and to show you some of the main runners and riders, I suppose, the main companies in that supply chain, from the materials up to the applications. With thanks to GTAT, a new silicon carbide substrate manufacturer, I've used their slides here to show the supply chain. And so at the start of the process, we need to be producing the substrates. As I mentioned before, the substrates are the material that gives us structural strength. They tend to be highly doped in themselves, so they're not really contributing to the working of the device, but we need them to build our device upon. And so we start with silicon carbide powder in the bottom left-hand corner. We put it into a high temperature furnace at 2000 degrees or more to form these large balls of silicon carbide. Those balls of silicon carbide get chopped into wafers, and those wafers or substrates are what I would start with in the clean room in producing a silicon carbide power device. Moving on to the next stage is we have to grow the epitaxy on the surface. We have to grow the lightly doped drift region, and that's done in a chemical vapor deposition, CVD system, to grow that lightly doped drift region on the top. And that could be 10 microns of growth if we're talking about a 1200 volt device. It tends to be a lengthy process in terms of loading your substrates into a chamber, getting up to temperature. The growth process is relatively slow. So this is a process that adds significant cost to the price of silicon carbide. And so getting CVD chambers with multiple wafers, with high growth rates, with high ramp up and ramp down times are all things that would potentially affect the cost of the devices, reduce the cost of the devices in the long run. We then get on to the fun bit. As far as I'm concerned, we then get to make the devices. So we've got our starting substrate, we've grown our drift region on the top, and now we can make the MOSFET, the diode, whatever it is we're going to produce on the front side. And that gets produced at wafer level before the wafer is then cut, diced into the individual chips. The individual chips are then placed into packages such as these, and then they're a bit more recognizable as a transistor as opposed to the substrate and the chip that we start with. And of course, finally, we end up with those chips going into modules, which then end up hopefully in something like an electric vehicle. So on to the supply chain and the people who are in it. So we start at the bottom of this with the silicon carbide substrate producers. And as I go through these slides, you'll see quite a few of the same names popping up. Chief among those is Wolfspeed. They have a very large share of the silicon carbide market, and are one of the largest suppliers of silicon carbide wafers and material. SiCrystal, owned by Rome. I'll try and point out as I go through, there have been a number of acquisitions and mergers along the way in the last few years, just showing how there's a lot of vying to be a vertically integrated company that can do all of this process. And Rome, way back in 2010, bought SiCrystal as a company to supply its own material. Rome are a chip manufacturer. Similarly, ST, the big chip manufacturer, bought Norstal, so they have a supplier of wafers and epitaxy as well. 26, SK Siltron, GTAT will all supply silicon carbide substrates as well. There's a new market opening up, of course there is, within China, and while I personally know less about the material myself, they're producing a lot of wafers at low cost, at high quantity to into the market as well. So SiCC, Tanker Blue are two of those. And the next step of the chain here, I point out the companies who supply epi-ready wafers. So wafers, silicon carbide substrates with the epitaxy on top. This is in the knowledge that some of those other chip manufacturers have this process in-house. These three companies listed here are the companies I would be going to purchase the epi-ready wafers, and that's Wolfspeed, Ascatron for very niche, very thick requirements, very thick epitaxy requirements for very high voltage devices, and SK Siltron, who are a Korean company who until this year were DuPont, and before that Dow Corning silicon carbide substrate epitaxy process. It would be remiss not to mention the suppliers of CVD epitaxy reactors. A couple of those names will be well known in the silicon world, Aixtron, TEL. There's a couple of other companies listed there who have very good reactors for silicon carbide as well, LPE, Epi-Luvac, New Flare in Japan. Moving on to the chip manufacturers, the companies that are producing the silicon carbide Schottkys and MOSFETs. What we have listed here in the top three positions are the vertically integrated companies, those that are fairly well covering the materials, devices and modules markets. And so we've got Wolfspeed. Cree nearly sold off Wolfspeed in the last few years to Infineon. Luckily for them, I think that was blocked by the US Markets Authority. And in the last couple of weeks, they've announced their intention to actually sell off the other half of their business, their LED business, to concentrate wholly on their power electronics market. That's somewhat surprising given that the silicon carbide power market was largely developed by them as a side product of their LED business, but now they're concentrating wholly on the power market. Rohm and ST Micro, Japanese and French-Italian companies, they are also fairly well vertically integrated because of their acquisitions, and so they are two of the bigger suppliers. ST have the contracts with Tesla and with a number of other big automotive suppliers. Also big suppliers in this market, Infineon and onsemi, who bought Fairchild in 2015. And you can see a host of fairly new entrants here on the right, or new entrants or smaller entities. Littelfuse have aggressively moved into this marketplace in the last couple of years. They bought in 2018 the startup Monolith Semiconductor and Ixis. So they are moving aggressively in this market. Microchip have started producing silicon carbide devices in the last 2 years. GeneSiC and United are fairly smaller entities. GeneSiC's a fabulous semiconductor company that's producing devices at slightly higher voltage. United are producing slightly different types of transistors, JFETs instead of MOSFETs. Listed at the bottom here, a couple of entrants in the market. Bosch came in recently. Max Power are another fabulous semiconductor company who are offering devices at a very low voltage. Alpha and Omega are a Chinese company largely supplying the Chinese market. It would be pretty hard in this time that I have to go through all of the applications. What I've decided to do is concentrate here on those applications companies that are very well integrated into the devices. And secondly, then I'll have a look at the OEMs, the automotive OEMs that are openly adopting silicon carbide. It's no surprise, certainly to me, in this left-hand plot of the device to application companies to see so many Japanese names. The Japanese companies look after their supply chain incredibly well. Toyota and their tier one supplier Denso have just rolled out this new company, MyRise Tech, to concentrate on producing all of their semiconductor processors. Mitsubishi are one of the only companies producing 3.3 kV devices, which it does for its own traction train inverters. So they produce the devices, but don't supply them externally, not to a great deal. Panasonic, Toshiba, Hitachi that have just bought ABB in the last couple of years for their power grids, the power grids arm of ABB. Those three companies are all very well integrated with the chip supply as well. Those companies between them developed a lot of the early IP in silicon carbide, as did GE Innovation Center are still active in producing silicon carbide devices. And I've mentioned already Bosch, who have started producing devices as well. CRRC, BYD, they show that there's this is a really colossal boom market within China as well. That should not be underestimated. The automotive OEMs adopting silicon carbide, or that there is information out there that they are doing so, I've listed here. It cannot be exhaustive. There are too many companies and not enough information out there, I would say. But top three there were the early adopters, Tesla and BYD in China. These are the ones who have openly adopted silicon carbide already, with you being able to buy, for example, a Model 3 today with a silicon carbide inverter inside it. Toyota have shown demonstrators of cars with silicon carbide inverters in them as well. It was recently announced a big contract for the Nissan Mitsubishi Renault group to start taking silicon carbide devices, which you can find if you just Google that. BMW, Volkswagen, McLaren, they're all actively involved in silicon carbide production. Just a couple of slides at the end to show what we're concentrating on at Warwick, which is a bit of a signpost for what's next, generally speaking. With the big name companies we've been through, concentrating on the marketplace of that 1200 volt, 1700 volt market space. We in the university sector, we like to look at what's coming next. And so distinctly what's coming next is higher power devices. So within 5 to 10 to 15 years, we would like to be pushing to see ultra high voltage devices being produced for traction applications for the grid, for transporting power over long distances. And so already in our clean rooms at Warwick, we're producing higher voltage Schottky diodes. We're producing MOSFETs and IGBTs at 10 kilovolts. And we're going to be moving on soon to be producing thyristors at 15 and 20,000 volts, 15 or 20,000 volts in a single, being supported within a single chip. Today, given the material that we have, these bipolar devices, the IGBTs and the thyristors, they require us to go through somewhat unconventional processing, but there's a lot of work to be done there to understand the technology now, to capture the IP in these areas, and to show the way for the chip manufacturers in the coming 10 to 20 years. One of the areas we're particularly passionate about is trying to get silicon carbide devices working in space. The big problem with space is that we have a lot of radiation flying around, a lot of heavy ions which are going to disrupt any devices that are up there and turn them on when they should be off, for example. And so a lot of the silicon solutions over the years have been developed to have some radiation hard tolerance. And so if we want to produce power supplies for space, which are smaller, lighter, more efficient, which we would clearly like to do in terms of our launch cost, then we've got to make our silicon carbide devices radiation hard as well. And at Warwick, what we're trying to do is to revisit the commercial silicon carbide topology at the moment, which is most certainly not radiation hard, and to redesign it in the same way that silicon has over the years to make it radiation hard. And so that's ongoing. We've got a new project starting on that next year, which will be producing new radiation hard silicon carbide power devices for real satellite applications. The Warwick Clean Room was built in 2010 specifically for silicon carbide power devices. It has everything in there that you would expect for producing silicon carbide chips. So we would take a silicon carbide substrate in. We have still currently the UK's only silicon carbide epitaxy reactor, the CVD system, for growing the silicon carbide drift layer. And then with that substrate, we have everything in-house to be able to produce a MOSFET, a diode, an IGBT, with the exception of the very specialist implantation process, which happens externally. Out of the end of that, we would have our silicon carbide die, which we can package in-house, and we would be doing the testing as well. Hand in hand with that is the design process, and we have a whole suite of servers there dedicated to the design and optimization of silicon carbide power devices. And finally, just a cheeky plug for my own silicon carbide consultancy firm. I have experience writing technology reports for OEMs on the silicon carbide technology. So that's covered previously for the silicon carbide materials from the substrates and the epitaxy, looking at the defects and the technology roadmap in more detail. Silicon carbide devices, when you would use each device, diodes, MOSFETs, and the roadmaps for those, packaging and modules and applications, and benchmarking to the other technologies that are out there, silicon and gallium nitride. I'm also got a lot of experience with device design and optimization and characterization as well, where that's helpful. I'm an academic. I've got a lot of experience in the market, so I'm open to other opportunities as well, be that from investors or other areas. With that, thank you very much. My LinkedIn address is there if you wish to contact me. Other than that, I will pass back to Jay.
Thank you, Dr. Peter. That was an amazing presentation. I have collected a few questions from investors, and maybe we can go through a few of these. The first one is, you mentioned various drivers for silicon carbide cost, how likely it is to go down as volumes grow, and by how much?
We're never going to see a parity in terms of the substrates with silicon. Silicon's this uniquely freakish material where you can just melt down essentially sand and produce this wonderful high quality material made of only one element. Silicon carbide, its production is harder, it's not as easy, and so the substrate costs are always going to be slightly higher. So we're not going to see parity, but we are going to see costs coming down as the whole field matures. I can't, as an academic, I don't think I'm in a good place to really tell you exactly where the costs will level out, but it's clear that we're still on a downward trend of prices now. We've seen ourselves that the cost of substrates have approximately halved over the last 5 to 6 to 7 years. So we're still going down in cost, but we won't be leveling out with silicon in a per amp cost basis. But it will naturally fluctuate to, I guess, somewhere around 150% of silicon.
Thank you. Next one is, what is the opportunity for someone like ST Micro to leapfrog other players? Can it be a true leader in silicon carbide after traditionally being a little more like second-tier player in semiconductors?
I almost consider that's a bit harsh on ST, to be honest. It's fair to say today one of the biggest players in power electronic devices, and that's certainly true of silicon carbide. If you see the deals that have been done, certainly with the automotive OEMs recently, ST Microelectronics name comes up very often. So they've had the first contract with Tesla, and there have been other contracts announced very recently with ST as well. I think it's fair to say there's a good battle going on at the moment for dominance in this market between ST, Cree Wolfspeed, Rome, and Infineon. They are four of the bigger players in this market.
Cool, thank you. Are there any new entrants coming into this field, and how likely they are to match the capabilities of current incumbents?
Yeah, there are some new entrants. The way the acquisitions and mergers have gone recently, we've seen a couple of new starters, new entrants into this market coming along and swiftly being bought up for their IP, for their services, for their offering, which sometimes the bigger company coming in don't have. So case in point is the recent acquisition of Ascatron by II-VI. That's so now II-VI have an Epi supply internally within their own marketplace, but there are still smaller players out there within the chip production process, like GeneSiC that I mentioned, the fabless semiconductor companies.
A big question is GaN on silicon carbide versus silicon carbide itself. Why do certain ones have specific use cases, and which one are the ones that are best suited for silicon carbide?
Okay, I touched something on GaN in my presentation, but I was referring to GaN in and of itself. But GaN does tend to be put on something. You don't get a freestanding wafer of GaN. So GaN as in and of itself refers to GaN on silicon typically. GaN on silicon is the preferred choice because you get a very cheap large wafer of silicon. You put GaN on the top, therefore you've then got a very large wafer of gallium nitride. They have their own spaces. So in terms of use cases, silicon carbide would be used at the high voltage end, gallium nitride potentially in the low voltage end, 100 to 600 volts, perhaps in the RF space. GaN on silicon carbide does exist, but it tends to be for very the very high efficiency, very good quality gallium nitride.
That's the end of all the questions I have.
Okay, Jay. Well, in that case, let me as an academic ask you, the investor, the question then. Where should I be putting my hard-earned academic money in this marketplace, do you think?
Well, looking at your presentations, you mentioned 3 major players and they are vertically integrated. They look quite strong in the areas of silicon carbide and design wins and what have you. So Cree, ST Micro and ROM, these are the major ones to start investigation in terms of investments. And then, as you mentioned, there are other players, new entrants coming in as well. So as an investor, one would have to keep an eye out for those as well. Thank you, Dr. Peter. To summarize the presentation, Dr. Peter talked about what silicon carbides are, why they are disrupting some areas in semiconductors, silicon carbide use cases and comparison with GaN devices, the manufacturing processes and quality issues, and some prominent players and market opportunity for potential investments. I hope this was useful to you. If you have any thoughts or feedback, please contact us directly on PI World website. A big thank you to Dr. Peter. If you need a deep dive in this area, I can highly recommend reaching out to him on his LinkedIn profile listed below.